So 7 million parameters, but only using 2 layers, but be able to beat 0.3 mini in Gemini 2.5 Pro on ARC AGI. But what makes it impressive is only using less than 0.1% of their parameters. Not by being clever, but by being recursive. So this model itself were built based from this whole idea in one picture. There's some fun input from XYZ, and it's recursive on this one tiny nut, and it gives you the refined answer. And for this case, the X or the embedded will be the puzzle you want to predict. It's the Sudoku. And it used from the predecessor TRM. The difference will be like here you can see the size itself using much more small parameters, but be able to giving an output with a higher accuracy. We can see the task itself. We try to remove one by one while backtracking solver verifies the solutions stay unique. The difficulty we consider will be this parameter. Easy we consider with this, medium consider with this, and so on. You can see that it backtrack from the solution itself. You can see. So this based only this clue, we try to predict this solution. And for the training TRM live, and for the training run, I'm using the exact paper scale. I already trained this for exactly 5 minutes, but you can actually try yourself with different parameters and a different training time. We can see that the held out evaluation, it showed that the accuracy giving almost pretty good, pretty nice. It's 90% plus, yeah. And the thinking part, we can show you that for the color code and for the bold will be the given clue, blue for the model field, red participating in a Sudoku, and the amber was will be the chain at his type. As we can see, for example, when we try to easy puzzle, the converts or the amber was will be converts easily at probably training time around 5. But if you try to show probably like the expert with, as you can see that experts show you that the self-given like the clue is very small, and for the convergence will take some couple times, and we can actually show you at couple set of time. For example, let's see at the 40 or 60, yeah, we can see that the model failed and the model conflict, but at the end you can see that it converts to the bare solution. And for the paper, I would like to talk some couple of question. For example, like does the latent actually approach a fixed point? If we force converts, does the answer get better? Or if we give the model longer at test time, will it actually give a better time or not? And finally, we want to see the whole computation, like the solution loss landscape as a rotatable 3D surface. So for the first part, will be the fixed point residual and the shape of the latent orbit. You can see that it does approach a fixed point, which is we can see for the easy and hard. It does reach at some point, will reach a fixed point. And how about we want to try forcing a fixed point? So we force him to converge. It can show you that converge variant burns many time more compute, but it does show you that it does give the same time, yeah, time converts and the exact fixed conversion time. And how about we give it more test time, recursion scaling? It does show you that it grow, but it does wobble and plateau rather than growing. So the tiny net can be run longer, but was never thought to exploit the extra iteration. So echoing from the paper finding that gains come from training with more recursion, not from spending more at inference. And lastly, for the landscape, the recursion actually travel. You can see that the line is the actual regression, and for the gradient, yeah, it is more like a gradient descent. So if the TRM were doing gradient descent on this landscape, it will slide smoothly downhill. Instead, it leap across basin, overshoot, and only settle once the puzzle is essentially solved. Yeah, for this takeaway, we can see that recursion is quite an architecture, and it does give some ID potential that not only giving more parameter, but implementing recursion does give some benefit itself. Yeah, for the on the bottom, yeah, you can just only press train, and all these part 2 train, it also will change based on the training we did here. Okay, I think that's all. Yeah, yeah, this paper based on yeah, less is more recursive reasoning with tiny network. That's all.